Okay, so I realized I just made a bunch of videos, and for some reason, my microphone was not hooked up correctly. I don't know why, so I'm having to redo them, okay? So we want to end up sketching the shear moment diagrams graphically, but before we do that, we're actually going to write the equations. So if you're a statics student and you're watching this, and maybe we are just covering through equations, you can stop. You can stop before we start doing it graphically at the end, okay? We will get to graphically, but for the sake of if you're trying to watch it for your homework, maybe just wait until we get to that in class. Okay? Sorry, I'm hungry. Okay. So before we can do anything, number one, we have to find reactions. Okay? And normally your problem statements are not going to say find reactions, but you just have to know that that's what you have to do. So I know that I'm fixed. I could have an AX, an AY, and a moment. Okay, resisting moment at my fixed wall. And I have 50 kilonewtons going up. And I have 60 kilonewton meters as an applied moment. I know it's because of units, I know that it is an applied moment. And then I have this that we're going to simplify. So it's just area under the curve is base times height. So I have 3 times 40, which is 120. And I also know that the centroid is, I don't know why this is not, there we go. It's right through the centroid is kind of at the center there of that rectangular piece. So we have 120 kilonewtons. And I know that it's going to be 1.5 meters, 1.5 meters, and 1 meter. So if I sum forces in the x direction, I'm going to find that AX equals 0. If I sum forces in the y direction, up is positive. I have my unknown AY, minus 120 plus 50 equals 0. AY equals 70 kilonewtons. It's a positive value, so it is indeed going up. I'm just going to go ahead and draw it on this because when I'm sketching this graphically, I'm going to have my reactions on here so that I can go through and make sure I have everything included on my shear moment diagram. Now we're going to sum the moments at A. And again, we could sum them anywhere, but just why not? I have that resisting moment at A, so I have a moment at A, okay? And with a moment, so we don't need to multiply by the distance. It will have the units of Newton meter. Okay, then we have minus 120 times 1.5 meters plus 50 times 3 meters minus 60 kilonewton meters equals 0. And remember, it's an applied moment. And if you don't understand that or remember that, look at your units. When I'm summing moments, I should have Newton meters. When I'm summing forces, it's only going to be things with newtons. So I have moment at A, I'm going to keep on this side, and I'm going to take everything else algebraically to the other side. So I have 120 negative times 1.5, 120 negative 1.5 times, okay, plus 150, okay, 60 minus, plus, and all of this goes over. I'm going to change that sign. So I have 90 kilonewton meters, and I assumed right hand positive, got a positive value, so indeed it is 90 kilonewton meters, okay? So the first thing we're going to do is we are going to write our equations, and then we're going to do it graphically, and then we can check our equations, okay? So again, if you're in statics, we haven't gotten to graphical yet, that's fine. Just go up to that point. So I can take a post-it note. You guys know how much I love my post-it notes. And if I'm here and I come across, okay, I have something happening here, so I'm going to go up with my shear. I'm going to have a negative 90. But as we're going across, I see I have that very uniform load, okay? Oh, and I had a change. So anywhere I have a change, okay, come across, come across, come across, and we are done. Anywhere I have a change, I have to make sure that I understand that's where I need to draw my free body diagrams and calculate internal shear moment. So I'm going to start with this first little area. It's 0 to x to 3 meters. Okay. And I think what I'm going to do is grab another sheet of paper and write on the back of it, because you can't see both. So let's just do this. That way you can see everything. So I need to cut it so I can take my Post-it note, cut it right there in the middle, and I need to have everything to the left. So I have my reaction. I have this rectangular load of 40 kilonewton per meter. My length of that base right now is x, because we're going somewhere between 0 and 3. I could have an internal normal, an internal shear, an internal moment. I have an applied 70 kilonewtons, I guess a resisting, and a 90 kilonewton meter. That's from my reaction. And it looks like I've kind of gotten everything drawn. Okay, so if I want the area of this, area is just base times height. It's x times 40, so I have 40x. And that actually is, if you think about the equation of a line, is y equals mx plus b. Okay, so we are creating the equation for our shear diagram. Okay, that's kind of what we're doing here, is creating that equation. And I know that the centroid has to be back x divided by 2. Okay, so I've got everything in terms of x and x over 2. So now I can sum my forces in the y direction. Well, first we'll sum forces in the x direction, and we'll find that our internal normal is 0. And really, if you wanted to get fancy, we could sum our torques, and we would find that we don't have any internal torque, which is good. It's a beam. So now we are summing forces up. So I have a positive 70, and then I'm going to come across, well, this shear is base times height minus 40x, okay, minus V equals 0. And again, this is positive by behavior, okay, positive behavior, but when I'm summing my equilibrium, I have to use the rule of up is positive. So even though it's a positive behavior, when I come to this step and I'm actually summing those forces, it is heading down. So for equilibrium, it is negative. I can pop that over, and I get that my shear equals 70 minus 40x kilonewtons. Okay. I can sum moments. I usually sum them about the cut. I just call it a dot right there. Okay. So if I start over here on the left, I have that resisting moment at the wall, which is a positive kilonewton meter, okay, minus this, okay, if I look at the cut, pin it, push up, negative, minus 70 kilonewtons, and its moment arm is x. It's constantly changing. If I'm at the wall, there is no moment arm. As I go all the way to 3 meters, we would have 3 meters, because x is from 0 to 3, okay. Now I have to take care of this. Well, I know that my area, it's making a positive rotation. My area is 40 times x. And if I look up here, that's exactly what I had for my shear equation. And then my moment arm is just x over 2. And as I come here, this shear is 0 away because it's at the cut, but I do have that resisting moment. Plus moment equals 0. And in this case, I have positive behavior. Remember, positive behavior makes compression top, tension bottom. And it's also positive because of the rule I'm using for equilibrium of right-hand rule. Okay, so that's positive. So I'm going to take everything else to the other side. Moment equals negative 90 plus 70x minus 20x squared. Okay, and again, kilonewton meters. Again, this is all for 0 to x to 3. And let's make sure we have all of it right. So we have a negative 90 minus 70 plus 40 plus moment, right-hand rule. So we're going to have a negative 90, a positive 70, and a minus 20 as we pull all of that stuff across. Okay, now we need to move our little Post-it note over, and oh, that's where we have our change. We have a applied point load right there. So I'm going to have a new free body diagram. Okay, and we're going to go past that applied point load, and I have normal, shear, and moment. Again, I always use right-hand rule. I have 50 kips pulling up. Okay, I have this uniform load. I have 70 resisting at the wall. I have 90 kilonewton meters resisting at the wall. X always starts at the wall and goes to the cut. Okay, that's X. But I know this is 3 meters because we've now got to include all of that. And if that's 3, this little nugget right here is X minus 3. So if we are going from 3 to X to 4, if X equals 3, 3 minus 3 is 0. So I am at this 3 meter point, okay? If I go all the way to 4, 4 minus 3 is 1. 3 plus 1 equals 4, and that would be the full length of my beam, okay? So I know that this load, it's all applied now because we've gotten past it, so everything is on here. My area is now a base of 3. My height is 40, so I have 120 kilonewtons. And I know it's going to be acting right here at 1.5 meters back. So if this is all 3, this is 1.5. And I like to just go ahead and label everything. So now if I sum forces in the y direction, up is positive. I have a 70 minus 120 plus 50 minus v equals 0. Again, positive behavior, negative according to this sign convention. V equals 0. Okay, so my shear, whether I'm at 3 feet or all the way to 4 feet, my shear equals 0. And that's okay. Sometimes that's the way it is. Let's sum our moments about that cut. So I'm just going to draw a dot. There's my dot. Okay, and I'm going to start with my clock handle. I have 90 kilonewton meters pushing this way. Okay, so that's a positive 90 kilonewton meters. Okay, I have 70 pushing it up, so that's a negative minus 70 times its moment arm is X. It's all the way from the wall to the cut. Come across, okay, I have this entire uniform load now. It's 120 kilonewtons pushing down, so we have a positive rotation. Move that out of the way, plus 120. And its moment arm is, well, if I'm at the cut, I have to go back X minus 3. And then I have to go back 1.5 meters, plus 1.5. So this becomes X minus 1.5. Okay. Then I have this 50. It's up, so we're causing a negative moment, minus 50 times, okay, its moment arm is X minus 3. And then when I get to the cut, I have this internal resisting positive moment, and all of that equals 0. So we're going to say our moment equals, all of this comes over, negative 90 plus 70x. Okay. Minus 120 times X minus 1.5 plus 50 times, that's a 50 times X minus 3, and all of that equals my moment. And if you go back up and look at your shear, I've got a 70 and an X, a 120 with something, and a 1, then that 50. So I've got everything pulled down, creating that moment. So we've got negative 90 plus 70x minus 120x plus 180 plus 50x minus 150. Now we have to start hoping that our math is right, okay? 70x plus 50x is 120x minus 120x is 0. Those go away. And I'm left with 180, a negative 50, so that gives us 30. 30 plus negative 90 equals negative 60. So this is just telling me that my moment from 3 to 4 is going to have a constant value of 60. And if we go back and look, we had a uniform load, which is a constant, and with our shear, we got a linear 1 degree. It's a linear. Here, we got a 2nd degree. So mathematically, things are working out correctly. I don't have any shear that I'm loading from here to here. Okay, so my shear is 0. There's no change. It's just constant. If this is 0, this is going to be, if you integrate and use your boundary conditions, you're going to get an actual value, okay? Because we're finding areas under the curves as we're moving down. Area under loading gives us shear, area under shear gives us moments. So how would I check all of this? The other thing is you have to notice when I cut this, I need to make sure I'm using some of this area on that little nubby part of the beam. I cannot go back here. Once I find my reactions and I've made this uniform load a point load, I can't look at that again. I have to redraw a free body diagram, because if I don't and I look at this 120, that means from here to the middle right here, I don't have any change in my shear because I don't have a point load. I'm going to need a completely different shear diagram. So behaviorally, I have to go back and consider that this is actually a uniform load. Okay? So, how would I graph this? Well, let's look at 0 to x to 3. And if I have shear equals 70 minus 40x, then when x equals 0, my shear equals 70. When x equals 3, my shear equals negative 50. Okay. My moment was negative 90 plus 70x minus 20x squared. When x equals 0, my moment is negative 90. When x equals 3, my moment equals, well, I have negative 90 plus 210 minus 3 times 3 is 9 minus 180. And that's a lot of math to do in my head. So I have 90, 210 plus 180 minus, and I get negative 60. Okay. If I have from 3 to x to 4, my shear equals 0. Okay, my shear equals 0. And my moment is just going to be negative 60. So now we can go back to our shear diagram, and we're going to draw it graphically, but we're going to check it with our equations, because we should be able to get everything on here. Okay, so graphically, shear, kilonewtons. I have a shear force that's going up. So I'm going to go up 70. And the reason it's going up is if this is up on the outside 70, internal has to be equal and opposite. That is a positive shear according to sign convention. Okay. If I have shear here that's going down, then I have to have shear going up. That's negative shear. So we can just follow the directions of our shear areas. So I have 70 minus this area. 70 minus 120 equals negative 50. Draw my little 150 right there. Okay, like so. And then I'm at negative 50. And I push back up 50 kilonewtons. So we end right here at 0, and I'm 0 across. If I look at what my equation said, I'm going to start at 70. I'm going to end at negative 50. Okay, and then I'm going to be 0 across. That's exactly what I would have. I know that where my shear equals 0, I have an important point. It's where my moment is changing from a positive to negative or negative to positive curve. Okay, it's where my moment slope is flat. So I need to figure out where this is. If I want to look at my equations, I have this handy-dandy equation, and I know that if shear equals 0, I could actually calculate where that happens. So 0 equals 70 minus 40x. So 70 equals 40x. X equals 70 over 4. 70, enter. Sorry, 40 divided by, and I get 1.75 meters. Okay, so that means at 1.75 meters, I'm crossing over. How would I do that if I didn't have equations? Well, I can look at similar triangles, and if you see this big purple triangle, it has a base of 3 and a height of, well, positive 70 all the way down to negative 50. 120 equals, and then I can go back and find this x. So let's do right here, this x X is to this height. X is to 70. And when I do that, I'm going to find that X equals 1.75 meters. So that's how I would do it graphically, is by similar triangles. Okay, so that means if that's a point that I need to know about, that 1.75 meters, then I need to take my moment diagram and I need to say, well, if X is 1.75 meters, what is my moment? Because that's going to be where I am changing from curve up, curve down. Okay, I'm changing that slope. Graphically, moment, kilonewton meters. I know that area under the curve makes shear, area under the curve makes moment. So I can go through here and find areas under the curve. So I have this area, I have this area, and then I have nothing. This is a negative area, and this is a positive area, and I like to signify those because I know where I have positive area, I'm going to have a positive moment slope. Where I have negative area, I have a negative moment slope. That doesn't mean my moment's negative. It just means that the slope is negative. So I could be up here with positive moment. It still has that negative slope. Okay, so area equals 1/2 base times height. So I have 1/2, 1.75 times 70. 0.5, enter. 1.75 times 70 times. And I get 61.25. 0.5, 1.75 times 70 times. Okay, and it is positive. Okay, so I'm going to be adding 2. When I look here at this, I have 1/2 base times height. So I have 1/2. Base is, well, if the whole thing's 3, this is 1.75. My base has got to be 1.25. And then I have negative 50. 0.5, 1.25 times 50, change signs, times, and I get negative 31.25. So that's the area. This is the area and the area under those curves. Okay, if you wanted to, you could put it in here of 61.25 and the negative 31.25. So as I start with my moments, I have a moment at the wall, and just remember, if the moment is coming this way, internal resisting equal and opposite, that's a negative moment according to sign convention. So we are starting at negative 90. Okay, and now I'm just going to run stuff in my calculator. So I have negative 90, okay, plus 61.25 plus negative 28.75, and I know that's going to occur right up here. So I have negative 28.75. I have this minus area, 31.25, change signs, plus, comes down to negative 60. And it stays constant at negative 60. Does that make sense? Well, over here at the end, okay, I have this external load that's being applied. You can't see that. Over here at the end, I have this external load that's being applied. See how it's going this way? So internally resisting. Okay, so we are coming up with that 60, and we close very nicely there with 0. So how do we know which way it goes? Well, if shear is 0, my slope is 0. That's one way. The other way is I look at this triangle, and if I want to do like a wedge in my triangle and a wedge in my triangle, does this have the bigger area or this? Bigger area, steeper slope. Smaller area, flatter slope. Bigger area or bigger area. Okay, this bigger, steeper slope. Flatter, 0. Basically, flat slope. So I know that it's going to curve up. And it's going to curve up. And the whole thing, it's all negative moments. But I have all of my critical points identified. 70, I have the 0 with the 1.75. I have the negative 31.25. I have my negative 60. I have where it crosses here. That's where my peak is at negative 28.75. And then I have this critical at the wall of negative 90. If I wanted to go back with my equations I could check my equations. I could, well, first off, what do we see here? Negative 60 is my moment from 3 to 4, and indeed it is. My shear from 3 to 4 is 0, and indeed it is.